about linear approximation and the derivative today. So as somebody asked me before class started, is the rest of the semester going to be applications of using the derivative? Pretty much. So today is going to be an application of the tangent line equation. So for 2/3 of the semester now, I've been having you find equation of a tangent line. Why, right? What's the point? So today we're going to talk about what the equation of the tangent line is useful for. So take 5 minutes or so and find the equation of the tangent line to the graph of f of x equals the square root of 1 plus x at x equals 0. All right, let's go through it together. So to find the equation of a tangent line, the equation of any line, you need the slope and you need a point on the line. So the slope we get by using the derivative, and the point we get by, I have one coordinate. How do I get the x coordinate, the y coordinate of a point on the line? Plug it into f, yeah. So I need a slope, and that's going to be my derivative at the x value of interest. And I need a point, 0, comma, f of 0 will be my point. Okay, so f prime of x, let's do that over here. I could think of that as 1 plus x to the 1/2 and apply the chain rule. So that's some stuff to the 1/2 power. So I'm going to have 1/2 times 1 plus x to the negative 1/2. But then I have to multiply by the derivative of the stuff. What's the derivative of the inside function here? 1. So I probably don't even need to write it down, but it's good habit. So then f prime of 0, what I get when I plug 0 in there would be 1 to the negative 1/2 is 1 times 1/2 is 1/2. All right, and then 0, comma f of 0, well, let's see, f of 0 I get by plugging 0 into my original function, which would be 1. So I have a slope and I have a point. This is 1/2 and this is 0, comma 1. I have a slope and I have a point. I want to write the equation that has that slope and goes through that point. So if I use slope, point slope form, saves me a little time rather than using mx plus b, though you can if you want. So I'm going to replace y1 with a 1, my slope with a 1/2, and my x1 with a 0, and I end up with y equals 1/2 x plus 1 when I solve for y. So that's the equation of my tangent line. I'm going to evaluate now for each of these x values. I'm going to plug it in to both the function f and the equation of the tangent line, get a y value for each. So if I plug in 8 into this original function, radical 1 plus x, becomes radical 1 plus 8, which is radical 9, which is 3. What do you get if you plug in 8 into this line? 5. 1/2 plus 8 is 4, plus 1 is 5. Okay, what if I plug a 3 into this radical function? 2. And if I plug a 3 in here, half of 3 is 1/2, plus 1 is 2/2. How about a 0? If I plug a 0 into the square root and a 0 into the line, what do I get? Nope, 1 and 1. Half times 0 is 0, plus 1 is 1. So 0.3, I might need a calculator. Making these small numbers here. So I'm going to take the square root of 1 plus 0.3. 1.14. And if I plug 0.3 into my equation, I get 0.5 times 0.3 plus 1, 1.15. And if I do 0.04, the square root of 1 plus 0.04 is 1.0198. And if I plug 0.04 into the line, I get 0.5 times 0.04 plus 1, which is 1.02. All right, so what do you notice about the y value of the function and the y value of the line? Can you draw any conclusions here? Always less. What's always less? Yeah, the function value is always less than the tangent line value. That's a good observation. Yeah, when x is close to 0, the closer x is to 0, the closer the two y values are to each other. 8, that's pretty far from 0, and f of x and the tangent line y values are pretty different, right? But then x equals 3 is closer to 0 than 8 was, and the two y values are much closer together. They're only off by a half. At 0, they are exactly the same. At the point of tangency, that makes sense because that point is on the line and the graph. So at the point of tangency, they are exactly the same. And if we don't go very far from the point of tangency, 0.3 or 0.04, the y values are almost the same. They're very close. All right, so let's take a little look at this picture so we can see what's going on here. All right, so I've got a graph of the square root of 1 plus x. It's just the square root of x, but shifted 1 to the left. And the green line is my tangent line. It's just the line that is tangent to this graph at x equals 0. And we already know its equation. So when I zoom in near the point of tangency, you can hardly tell the green line from the blue line. Right? So when I'm really close to the point of tangency, the y values of the green line and the blue line are almost the same. Right? And then as I get further apart, like when I go out to 8, right, then they're pretty different. But the closer I get, the closer these two lines are getting to each other. Same thing from this side. Here they're pretty far apart, but then as I get closer, they get closer together. And when the x value is close to 0, the original function and the tangent line are pretty close together. So that means we can use that tangent line to approximate the function value. So the goal of this section is to be able to approximate y values of points on a curve, to approximate y values of some complicated function with y values of points on a tangent line. Because tangent lines are lines, and lines are really easy to work with. Really easy to plug a number into a linear function. So this is the basis of how a lot of approximation was done before calculators, right? If you wanted to know the square root of 1.3, that was a difficult calculation. So this was one way we could do it. Get a tangent line approximation at 0 and plug 0.3 into the tangent line, and you'd have an approximation for the square root of 1.3. Okay, so we want to go back and find the percent error for each part here. So remember, percent error is, how do I calculate percent error? Somebody remind me. Yeah, so the amount of error would just be, right, one minus the other, right? So this is my exact value is 3, my tangent line approximation is 5, so I have an error of 2, right? But then how do I find what percent off am I? Divided by something, 3. Divided by the actual value. So percent error we calculate by doing just amount of error divided by actual value. All right, because we want to know how far off we are from the actual value. So you compare your error to the actual value, and you got to multiply that by 100 to get the percentage. So in this case, I would have 2 divided by 3, which is a 66.67% error, which is pretty big, right? And then in my next one, when x equals 3, my amount of error is a half. I'm off by a half. But I want to compare that to the value I was shooting for of 2, right? So my percent error, 0.5 divided by 2, is 25%. Big jump in closing the error percentage. All right, what's my percent error in part C here when x equals 0? 0%. I'm not off at all, so my percent error is 0%. All right, so in D, my amount of error is 0.01, right? And then I just need to divide by the actual value of 1.14. .01 divided by 1.14, and I get 0.877 as my percent. So less than 1% error now. So I'm really close. And then finally, in this last one, when x is very close to 0, my difference, 1.02 minus 1.0198, is 0.0002 is my error. Divide that by the actual value. And I get well, I should change it to a percent. So that would have 3 zeros, but now it's just going to have 1 when I multiply by 100. Less than 0.02% error. Okay. So your book goes through the same idea with the function sine of x at x equals 0. Take a few minutes, find the equation of the tangent line to sine of x at x equals 0. All right, so looking for the equation of the line that's tangent to sine of x at x equals 0. So if I just sketch a little picture of sine x, something like that, I'm looking for the equation of the line that's tangent to sine x at 0. Okay. So again, I need the slope of that line, and I need a point on that line to write its equation. Now, what are the coordinates of that point there? 0, 0. Okay, so I've got a point, 0, 0. And then the slope of that line I get by taking the derivative and plugging in 0. So f prime of x is cosine x, and f prime of 0 then is the cosine of 0, which is 1. So then just for the heck of it, out of habit, I write down the point slope formula, but then I'm going to put in a 0 for y1 and for x1, because the point I'm using is 0, 0, and a 1 for m, so I end up with y equals x, is the equation of this tangent line. Okay. So that means that near x equals 0, y equals sine of x and y equals x are indistinguishable from each other. It is a good approximator. So if I draw a little box around there, the pink line and the purple sine graph lay so close to each other that the difference in y values is very small. Okay, so sine of x is approximately equal to x for small x's. So let's just check this conclusion that we've had by taking the sine of some small values. Make sure you're in radian mode. Yep, okay. All right, so the sine of 0.5. I mean, that's, relatively speaking, close to 0, right? 0.479, that's pretty close to 0.5. If I round it, it's 0.48. Right? So it's off a little bit, but it's a pretty decent approximation. And then if I go even closer to 0, 0.02, I get 0.01999. Really close approximation. And the sine of negative 0.007. So I'm even closer to 0 now, and I get negative 0.0069999. So really, really close to the x value. So this idea that sine of x is approximately equal to x for small x's turns out to be really useful in some physics calculations. So keep an eye out for that if you're taking physics. And it's often not explained when you're doing the physics calculations of why you can substitute, why they are nearly equivalent, sine of x and x. And it's because y equals x is the equation of the tangent line at sine of x at 0. So the general form for the tangent line is called the local linearization sometimes. The local linearization of f near a point x equals a is this formula. And it just says that you can approximate f of x by using the equation of the tangent line. So this guy is just the equation of the tangent line. At x equals a. So the local linearization just says if you want to know the value of f of x, you can approximate it. That's why I have the squiggly lines there. You can approximate it by plugging a into the tangent line equation instead of the equation for f. All right, so time for you to do one for practice. Find the local linear approximation for x times 2 to the x and use it to estimate f of 1.01. Okay, so find the local linear approximation. That is fancy talk for the equation of the tangent line, right? So I'm looking for the equation of the tangent line to f of x equals x times 2 to the x at x equals 1. So to find the equation of a line, you need a slope and a point. The slope we get from the derivative. So my slope is going to be f prime of 1, right? Just take the derivative, plug in x equals 1, and we got the slope of the tangent line. And then my point I get by taking the x value they gave me and plugging it into f. Because at the point of tangency, that point will be on the line and it will be on the graph of f. So I can get the coordinates of that point by using the f value. So this is going to be 1 comma f of 1, which is going to be 1 comma 2. We plug a 1 into f. All right, so I've got my point. Now I need my slope, which I will find by finding f prime of x and then plugging in a 1. So this is a product, x times 2 to the x. So to find the derivative, I need the product rule, which says first times the derivative of the second, and the derivative of 2 to the x is 2 to the x ln 2. First times the derivative of the second plus the second times the derivative of the first, and the derivative of x is 1. All right, so then I just got to plug a 1 in there. So this is 1 times 2 ln 2 plus 2. So 2 plus 2 ln 2 is going to be my slope. All right, so equation of a tangent line, y minus y1 is m times x minus x1. It's the equation of any line, point slope formula. So I'm going to replace m with a 2 plus 2 ln 2. And x1 with a 1 and y1 with a 2. Just move the 2 over, and I'm going to have, see if I distribute this, I get 2 plus 2 ln 2 x minus 2 minus 2 ln 2, and then we have a plus 2, so this is minus 2 ln 2. Yeah, that's good. That's it. Everybody see what I did? I did like 3 or 4 steps in one there. All right, so that's the equation of my tangent line. So I'm now supposed to use it to estimate f of 1.01. So what it turns out that I can do is, instead of taking f of 1.01, that should be approximately equal to what you get when you plug 1.01 into the tangent line. And I'm just calling the tangent line y. Right? Why do I know that those will be approximately equal? Yeah, because my point of tangency was at 1, and 1.01 is pretty close to the point of tangency, so I know that the tangent line will be a decent approximation. You have to be near the point of tangency for the approximation to be true. All right, so if I plug 1.01 into my tangent line, all right, so I have 2 plus 2 ln 2 times 1, I should get that value first, times 1.01 minus 2 ln 2. So 2.033. 2.034. All right, so there's my approximation for f of 1.01. Is it an overestimate or an underestimate? Under? How do you know? How could we find out? Evaluate the original. Yeah. So I want to do 1.01 times 2 to the 1.01. Oops. There we go. 1.01 times 2 to the 1.01. And I get 2.034, but the other one was a little bit smaller than that. They look equal because I rounded. This is 2.0339 if I go out one more place, right? And then the actual value is like 2.034. F of 1.01, 2.034. So this is an underestimate. Okay. How good is it? What's the percent error? So I'm gonna do percent error on my calculator, and I'm gonna keep all the decimals so that I can be accurate about it. So I want to subtract that 2.033869294 number from the 2.034. So new minus. I didn't save that number. If I had been thinking ahead, I would have stored it as A or something, but I didn't, so I'm going to type it again. Okay, so that's my difference in the two values. And then I'm going to divide by the actual value, which is the 2.034050211 times 100. So it's 0.0092% off. Under, yeah, it's 0.0092 below the actual value. So let's take a little look at the graph of f of x and the tangent line at x equals 1. I'm going to use Geogebra to look at these. Make the fonts bigger. So f of x equals x times 2 to the x. All right, so here's my function. I'm interested in its tangent line at x equals 1. So I'm just adjusting the window so that that'll be easily seen. All right, that's good. And then the equation of my tangent line was 2 plus 2ln 2x minus 2 ln 2. Right, that was it. Yeah. Okay, so there's my tangent line at x equals 1. So let's plot the point. So there's my point of tangency at A. Could you have predicted that this tangent line would give you an underestimate before plugging in to the actual value? Yeah, how? But if you look at the graph, yeah, because the graph of f is concave up, right? And the tangent line has no concavity. It's always going to be below the graph. So the y values on the line are always going to be below the y values on the original function. Well, right, yeah, if it was above, it wouldn't actually be a tangent line, right? What if the graph was concave down? What could you say about the tangent line approximations? They would always be overestimates because the tangent line would lie above the curve. So if a function is concave up, the linear approximation underestimates the function because the tangent lines would all lie below the curve if it's concave up. And if the function's concave down, the tangent lines will lie above the curve and the linear approximation will always overestimate the function value. Okay, so now we define the error in a local linear approximation. We've already been doing this as the difference between the actual value and then this whole notational mess there is just the value you get when you plug A into the tangent line. So this is the tangent line approximation. Okay, so the error is just the difference between the two. So when we're close enough to A, the error has to get really small. When you're close to the point of tangency, the error goes to 0. So this explains why the graph looks why any graph looks like a line if you zoom in enough. Okay? But saying that the limit as x goes to a of e to the x equals 0 is not enough, right? It can't just be that the error goes to 0, because otherwise I could use radical 1 plus x approximately equal to 1 as my tangent line approximation, but that is not, because radical 1 plus x does go to 0 as x goes to 0, but that's not a very good approximation. So it turns out that we have to say something a little bit stronger about what happens to the error. It does have to go to 0, but it has to go to 0 very fast. Okay? So it turns out that if I look at the limit as x goes to a being the point of tangency, of the error over x minus a, that has to go to 0. Right? And that means that e to the x, the numerator, would have to go to 0 faster than the denominator does. Right? Because if the denominator went to 0 faster, then that whole fraction would blow up to infinity. So for that fraction to go to 0, the numerator has to go faster than x minus a does. So that shows why any differentiable function, no matter how weird, if you zoom in far enough, it just looks like a line. And that line that it looks like is always the tangent line. All right, so there's some problems I want you to work on out of your textbook. If you don't have it, I can call it up on the computer so that you can see it on the screen up here.